Hello. In this presentation, I am going to tell you a little about rotation and translation metrics. So these are the contents which we are going to study today. This is a translation, rotation, and then the derivation of rotation matrices. Translation. The dictionary meaning of translation is to move from one place to another. You can also say that it is a geometric transformation that moves every point of a figure or a space by the same amount in a given direction by adding a constant. Now here's a keyword here, by adding a constant. Please remember this, we will be going to use in a while. A translation is an affine transformation with no fixed point. Now there is again a keyword here, no fixed point. There is no fixed point in translation at all. Each and every point will be going to move. So let us understand 1D translation first. Now, by suppose there is a guy called John. Now, John is standing on a one-dimensional coordinate system at a very arbitrary point, say 1.586, in the coordinate system A, right? Now, you want to meet John, right? So, it is a very weird position. So, I said, John, why don't he move to origin? But John is very lazy. John said, no, he don't want to move. So I came up with the idea, why don't I move the origin to the John instead? And to do so, I have to subtract each and every point of coordinate system A with a constant, remember? And in this case, that constant is 1.586. So if I subtract each and every point in A by 1.586, I will get a new position of origin in a new coordinate system, say B. And in this coordinate system, John is standing at origin. So if I say that John is standing at 1.586 in A, or I say John is standing at origin in B, they both mean the same position of John, right? So let us go to 2D translation. Now, now John is standing in a two-dimensional coordinate system, local coordinate system, right? And you know his position. But some foreigner guy called you. He follow the international coordinate system, say B. So somehow, and he wants to meet John, right? So somehow you have to develop a model so that you will give him position of John in your coordinate system, and he will get the position of John in his coordinate system. And to do so, we will subtract each and every point in A by the difference of origin. And it can be done like the previous. It can be done like previous with one axis at a time. Either you can go with x-axis first, then y-axis, or y-axis first, then x-axis. The key here is they both result in the same position. So we can say that translation is commutative. Now it is more preferable that why don't we do both the things simultaneously? And it can be done simultaneously by using a matrix. And similarly for 3D, we will add another row of Z and it will become a 3D translation matrix. Rotation. Rotation turns an object about a fixed point, a fixed angle. So there's a fixed point in rotation, that is origin, but there was no fixed point in translation. Rotation matrix rotates points in counterclockwise direction through an angle theta about the origin. So rotation matrix is either rotate the object counterclockwise or rotate the object clockwise. They both mean the same thing. Rotation matrix is orthogonal as well as unimodular. That is transpose of rotation is equal to 1. So let us understand first what rotation is doing. Then we will go further. So this is our reference figure. Now when we rotate this is our rotation matrix for x-axis. So if we rotate in x-axis by 90 degree using this rotation matrix, so we will get final figure like this. Or you can also say that either it is moving object counterclockwise or it is moving coordinates clockwise. They both will end in same result. So they both mean the same. A rotation matrix is used in both ways. Similarly, when we rotate around y-axis, we will get something like that, and the anti-clockwise movement in according to along y-axis. Similarly, in z-axis, and the anti-clockwise movement in along z-axis. 3D rotation. Order of axis in which you rotate is important. Changing the order of rotation changes the final location of the object. That means that rotation matrices are not commutative. So if you analyze this figure, you can see that changing the order of rotation changes the final position of object. So if nothing is given, we can say that correct order is along z-axis first, then y-axis, and last axis. and last x-axis, although there is no correct or incorrect, but this sequence is preferable. Transformation is a combination of rotation and translation. Whether you rotate or translate first is also important. That means transformation is not commutative. So if you analyze this slide, you can see that either you translating first or rotating first. They both will end up in different location of the object. So they are not commutative. So if nothing is given, correct order is rotation first, then translation. Derivation of rotation matrix. I have taken it from a YouTube source. Okay. Now John is standing in a two-dimensional coordinate system. So now you don't want to meet John. You want to go to the position of John, where John is standing right now. Okay. So John can go now. Now you know the coordinates, his coordinates in local coordinate system A, but you want to transform this coordinate in a international coordinate system, say B, and the angle between your coordinate system and B coordinate system is theta. Right. So we will draw a line perpendicular to xb, and again we will to meet at A, and then we will draw one more line parallel to xb to meet at P, and we will extend this line and draw a line parallel to xb so that they will meet at D. Now this rectangle is the key here. If you can make this rectangle, you can easily derive this equation. So in triangle OBA, OB is equal to OA cos theta, or OB is equal to XA cos theta, and so and in triangle ADP, AD is equal to AP sin theta, or you can say AD is equal to YA sin theta. But by our rectangle, we know that BC is equal to AD, so we can replace what is XB, OB plus BC. Okay. So when we add OB plus BC, and we know BC is equal to AD, so we can write XB is equal to XA cos theta plus YA sin theta. Now similarly we will do for Y, right? So YB is what? Look at the figure. YB is PD minus CD, right? And CD is nothing but what? AB. So we can say that XA sin theta is equal to CD, and this is and YA cos theta is equal to PD. Then we minus PD minus DC, and we will get the coordinates for YB. So the final result will something look like this if you do it by yourself. So, and this equation can also be put into a matrix like this. Now in this case, the coefficient of XA and YA is known as rotation matrix. Please remember that while we are deriving, we rotated the axis counterclockwise, but the positive is clockwise. So this will give the result in negative direction. And to make it positive, we will replace theta by minus theta. So this matrix will give result in positive direction. Now, actually we were working in 3D already. We were moving along z-axis, and so when we rotate along z-axis, then the coordinates of z will not change. So to make it 3D rotation matrix, we will along z-axis we will add at the end one row and at the end one column, so such that z will not change. So it will look like this, and this matrix will rotate along z-axis. Similarly, when we rotate along y-axis, coordinates of y will not change. So we will add a row and column in the between, such that y will not change, and similarly for x. Now, all the axes rotate in positive direction. So we generally follow right hand rule for coordinate system, and left hand thumb rule for movement of coordinates. So by positive y means, by following left hand rule by positive y means it is clockwise in z-axis, anti-clockwise in y-axis, and clockwise in x-axis. And so that to make the y-axis also clockwise, we replace theta by minus theta. And we will, when we do so, we will get our final form of matrices like this. And in this case, these matrices will rotate coordinate clockwise or the object anti-clockwise. All these matrices along the x, y, and z direction. Generally in GPS and you can say GIS, the rotation of coordinates is very often used. So it is also used. It is also very useful for the rotation of coordinates. Thank you.